Okay, so when we're doing an experiment like the caffeine experiment, there are four main ideas to make it valid. Okay, and the first one is we need to take care of extraneous variables, which is a variable that is not of interest in the current study but is thought to affect the response variable. We need to be aware of extraneous variables for two reasons. One, extraneous variables have the potential to become confounding variables. And what I mean by that is an extraneous variable is anything that might affect results. If you can set up your experiment to make it not interfere, then it's just extraneous. The minute that it might actually interfere, now it's confounding your results. So a confounding variable is one that has actually affected it. Extraneous just means it's extra, but maybe we could take care of it. To prevent sugar from becoming a confounding variable, we need to make sure that both treatment groups get the same amount of sugar. So here's the deal. If we gave them Coke and caffeine-free Coke, the only Coke that's caffeine-free is diet. So giving one group Coke and one diet caffeine-free would mean that there's an extraneous variable in there because the people that got caffeine also got sugar. So to prevent that, you'd give one group diet Coke and one group diet caffeine-free Coke. That's how you prevent extraneous variables from becoming confounding. All right, the other thing is that extraneous variables create extra variability in the response variable, making it harder to estimate the effect of the treatment. So here's the deal. If we let subjects drink soda in any weight they want, the changes in the pulse rates will probably be more variable. If you down a cup of soda, okay, versus you sipped it over half an hour, at the end of a half an hour, the person that downed it is going to have more caffeine in their system than the person that was sipping it. So again, it's another extraneous variable that if we don't take care of it, becomes confounding. So the two sets of plots below have approximately the same centers, but much different amounts of variability. Which set shows that the second center is higher more convincingly? So let's look at the first set. Okay, so we have A and B right here. Can you tell which one has a higher average caffeine? So you guys are thinking 2, but look at how spread out it is. Okay, what if I took off these two? Now could you tell? Not really. There's a lot of variability. Turns out that A was the no caffeine group and B was the caffeine group. Here's where their centers are, and it is that the caffeine has a slightly higher center. But again, there's so much variability that it'd be hard to tell. The next set of data, they limited a bunch of the extraneous variables, specifically time. And I've been told that this is real data from a class that did this. Do I know that? I don't know, but that's what I was told by the person that gave me this, okay? You can see that they both have about the same center. This one was 110, here was about 110, about 100, a little over 100. But there's more consistency and less variability. So I'd be clearly able to say, hey, the thing that caused this one has a higher center, and it probably was caused by the caffeine. The next thing we want to look at is direct control. Direct control means holding extraneous variables constant for all treatment groups so their effects are not confounded with the explanatory variable. This eliminates variables as sources of variability. So that's the idea of making sure we do diet Coke and diet caffeine-free Coke. Everything that we can control, we do to reduce that variability. What do you guys think would be some examples if we had done that study of things we would need to control? So we already said sugar, right? And the time it takes them to drink it. What else? Previous activity level, yeah. If you were out in the hall doing jumping jacks, or you had a gym class before math class, your heart rate's already up there. You're already stimulated. If I give you caffeine, it may not go up that much higher, or it may go up way, way higher. One, I don't know, but it adds an extra issue. What else? The amount, absolutely. Amount consumed. Tolerance level, right? If you drink a Mountain Dew or a coffee every day, giving you a little bit of Coke may not affect you. But if you believe in not drinking caffeine and then I give you a little bit of caffeine, your body might react extra strong, right? What else? Resting pulse rate, yep. How about gender? We don't know. I don't know if boys metabolize caffeine different than girls, but I do know, especially at your age, you guys have massively different hormones running through your body, right? Girls are getting flooded with estrogen and boys are getting flooded with testosterone. Maybe that affects the metabolism of caffeine. So maybe gender. Again, anything we could think of. Age, absolutely. How about weight, body mass index? Okay. Are you solid muscle or are you solid fat? Your body metabolizes differently, right? So all of these things could affect it. And your goal then is to even out the treatment groups. So that maybe you'd group them by gender, but then, and maybe you'd group them by age and by body weight, but the things that you can't group by, you'd want at least the same mix in each group. Does that make sense? So you don't get all the fat people in one group and all the skinny people in another group. You'd want to mix up. Because then, yeah, there's some variability, but they're the same variability for both groups. Let's see if we missed anything. Brand of soda. Maybe Pepsi is different than Coke. All right. Time of the day. Are you doing this in the morning or the evening? Empty stomach or full stomach? Did you just have lunch? Okay. And the bottom line is there are so many extraneous variables, we can't account for all of them. Somebody else could walk in and have a new one that we didn't think about. So that's why we try to do everything randomly. We account for what we can, control what we can, and then the rest we hope that using a random sample will mix up all the other ones evenly. Okay. The next thing is randomize. Okay. Random assignment of subjects to treatments to ensure that the experiment doesn't systematically favor one treatment over the other. Okay. What about all of the other extraneous variables we do not think of? What about the variables we cannot directly control or block for? What if a critic reads your study and says, what about this variable? And we say, you're right, we didn't think about that, but we randomized so it was taken care of. Okay. Now, they said or block. Block is something you're going to learn about. That's like stratifying for experiments, okay? And that's new vocab words. Everything we do with sampling, we will change and we'll do the same thing for experiments, but we'll call it by different names. So if you're sampling to do a survey, you would use the word stratify. If you're setting up an experiment, you do the same thing, but you'd use the word block. So chapter 13 will have its own vocab words, but same ideas. All right. If we randomly assign subjects to treatments, this should balance but not eliminate the effects of these variables, since their effects should be equally spread between the treatment groups. Note, we must always randomize, since there will always be extraneous variables we do not consider. Randomizing guards against what we don't know and prevents people from asking, but what about this variable? How do we randomize? Okay, we can do blocking. We'll talk about that later. But inside of that, simple random sample, random number generator, something that's truly random, right? None of this, I think you go here, I think you go there. We learned about that with the Gettysburg Address. That builds in bias. The third principle is replication. There are two definitions for replication. The AP definition is that it ensures that there's an adequate number of observations in each treatment group. So if you only had 2 people drink caffeine and 2 people drink the placebo, okay, what if those 2 people in the caffeine group have a high tolerance? Then that's going to negate your study. You have to have enough people in each group. So replicatable per treatment group. The other version of it is this. You repeat it and get the same results. So in the real world, let's say I'm up at the U and I do a study, okay, and I get these results and I prove that caffeine makes your heart go faster. Well, now another college somewhere else is going to look at my experiment design, do the same thing, and see if they get the same results. And having it replicated over and over and again in valid settings adds weight to your results. So there are 2 forms of replication, 2 definitions. When AP is talking about it, they're talking about having enough people in each group. Okay, but in the real world, we have 2. Okay. Lastly, never mind, not lastly. Increasing the group size makes randomization more effective. So just what we're saying, the more you have in each treatment group, the more likely those other extraneous variables are mixed up, because you have more people that have those extra things. Does that make sense? All right. This was talking about the other definition. Replication can also refer to repeating the experiment with different subjects. This can help us feel more confident applying the results of our experiment to a wider population. So we do it here in Utah, then they do it in California, then they do it in Florida. They all get the same results, and we're able to say, hey, maybe this is true for everybody in North America. Summary. With control, blocking, randomization, and replication, all these things we'll learn about, each treatment group should be nearly identical, and the effects of extraneous variables should be the same in each group. Now, if changes in the explanatory variable are associated with changes in the response variable, we can conclude that it's cause and effect. Otherwise, we just have to say, oh, look, that's interesting. Looks like it, but have no idea. Okay. If we had done this caffeine experiment, how could we have randomized? What do you guys think? So pretend that if we'd had time, we would have. Pretend that we did this as a class. How could you randomize? Right, but even more specifically, like now we want to control for variables. I would maybe split it between boys and girls. If we don't want to assume boys and girls are a gender thing, then we won't. Maybe split it between who regularly has high caffeine and who regularly doesn't. Some type of blocking. And then in each group, I couldn't do blocking for everything. Why not? You divide it too much. If we blocked it by gender, and then we blocked it by how much caffeine you have and all of that, all of a sudden you've got 1 or 2 people in each group, and then you don't have replication. So block it by a couple things, then do a random sample, true random sample with a simple random sample, random number generator, and decide who in each group gets caffeine and who doesn't. Does that make sense? Okay. All right. Not all experiments have a control group, a placebo. Okay. But as long as there's comparison, we're good. For example, if they're testing a new drug, it is usually compared to the current drug. If they had a new type of aspirin, they wouldn't give one person the new drug and one person a sugar pill. They'd give one person the new drug and the other person aspirin. Okay, so that's how they do it as a control instead. It's not always a placebo. Okay, and then there are also ethical issues. Will it harm people doing this experiment, such as the smoking in the mothers, right? And so maybe you have to do a placebo for health issues as well. Finally, the results of an experiment are called statistically significant if they are unlikely to occur by random chance. For example, if caffeine really has no effect on pulse rates, then the average pulse rates of the 2 groups should be the same. However, because the results will vary depending on which subjects are assigned to which group, the averages will differ slightly. It depends on how much they differ. Does that make sense? And is this differing likely to occur by random chance? Or is it such a big difference where like that couldn't have just been random? It must be the caffeine. Okay, and we'll learn about that in quarter 4, how to decide how much is enough. This right here should say random chance, not change. All right, for those of you that aren't here, as a class, we're going to look at number 7 through 13, and they're just going to put it on the top of their homework number. So for you guys, it's homework number 10. Okay, they're going to put 7 through 13 and say if it's an observational study or an experiment. They're not going to answer any of the other questions about that, and as a class, we're going to go through it, so you guys can come ask me about it. Then you'll start homework number 11. You will only look at 11, 14, and 16, and for those, I'm telling you they're experiments, so you only do B, C, D, and E for experiments. Each one of these questions has lots of little questions, only do the ones specified. And then you'll also do 32, 34, 41, 47. So those of you that are in class, go ahead and start doing 7 through 13 on the top of your homework. Those of you that are out of class, you need to watch the other video and also do 7 through 13 plus the homework. I also left out 35. Go ahead and look at 35 in the back of the book, those of you that are not in class. Thank you.